Hello, my name is Jacob Dye, and today I'm going to talk about Lab 3 for Physics 2212. So our main objectives are to determine the distance dependence of the magnetic field of a small bar magnet. Then we're just going to measure the magnetic field of a magnet on axis and off axis using the PHYS law of magnetic fields. And then we're just going to simulate the magnetic field using GlowScript and then compare both experimental and our computational model. And also we have our findings, which I'm going to explain at the end. So first we have our formula for dP, which is the magnetic field for a small section of magnet. And it's important to know that the distance far away from the loop and through the center of the loop, the magnetic field has the shape of the on-axis magnetic field of a dipole. We have both formulas next to it. And then the magnetic dipole moment as formulas as well. And also the direction of an on-axis magnetic field is the same direction as the magnetic dipole moment as well. So another key concept, we have our magnitude of a magnetic field of a magnetic dipole on the perpendicular axis. We have our magnitude of a magnetic field of the bar magnet, which is the magnetic dipole. And we also have a general formula for the magnetic field of a magnetic dipole. So for our visual model for magnetic field, first we have our system, which is the observation point, aka the magnetometer. We also have our surroundings, which is the bar magnet producing the magnetic field. And it's important to know that we treat the bar magnet, as a magnetic dipole. And as you can see in the picture, the magnetic dipole and the magnetic field, they both go from south to the north pole. So just to go quickly of our procedure, first we have our materials, which is the bar magnet, the magnetometer, and the meter stick and tape. And we also compensate for magnetic north using the magnetometer app. Then we just find the magnetometer chip, and then we just measure the on-axis magnetic field. And afterwards, we measure the off-axis magnetic field. And here we have our results for the experimental portion of the lab. And note that the line of regression and the decrease in distance between the magnet and the magnetometer as the magnetic field increases. Also note the off-axis magnetic field measurements at the bottom of the screen. Also, the following equation is equivalent to the regression line from the data, the one in the picture, and the slope of the regression line equals n, and the y-intercept equals ln of k. And then we just solve k using the inverse constant and the exponential function. And then by using the constant derived from the regression line, the following equation can be used to solve the magnetic field. Also, more observations from our analysis, and when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the measured x component in the field increases, as you can see in the table in the right. So to begin with our computational model, which is we first put in our physical constants, then we create our magnet at the origin, and then we just edit a function to create its magnetic field. Then to visualize the magnetic field, we scale the arrows to fit in the screen and its distance as well. And then we just put in the observational location for the on-axis and the perpendicular axis. And then we just draw the arrows to represent the magnetic field on axis. Then, similar to before, we put in arrows to represent the magnetic field perpendicular to the axis this time. And then we just put the average, the perp from the experiment, and then also the observational location at 45 degrees from the axis. And then finally, we just draw an arrow to represent the magnetic field at 45 degrees from the axis as well. So after we rerun the program, here we have our results. We have our magnetic field for on-axis and perpendicular axis for different measurements. We also have our distance and the magnetic field at 45 degrees within component form. So first of all, as the distance between the magnetometer and the magnetic decreases, the magnitude of the magnetic field increases as well. And we have our magnetic dipole moment, which is 1.49 amp squared. And we have our experimental magnitude of the magnetic field of axis. And we also have our simulated magnetic field of axis. And as you can see, there's an 86% difference in the net magnetic fields between the computational and the experimental model. So to go quickly, here we have a few sources of error. We may have other sources of magnetic fields distorting our measurements. We may have inconsistent placement of the phone, and maybe the surface we were measuring was not completely flat, and maybe the measurement with the magnetometer may not have been very consistent, and the measurement error when determining distance between magnetometer and the magnet may not have been very accurate as well. So for our first what-if question, and for the sake of time, I'm not going to read the question, I'm just going to answer it. So the measured magnetic fields would be different due to not accounting for the magnetic north. And the x component would be different because magnetic north would contribute to the magnetic field measurements. Also, the components would also be different due to not accounting for the magnetic north. And at an intermediate angle, magnetic north would contribute to both x and y components of the magnetic field. And since we're in a flat surface, this z component would not change. And to answer the second question, the magnitude of the magnetic field would increase due to the combined magnetic fields of the two magnets, and we would expect the magnitude of the new magnetic field to be approximately double the magnetic field of one magnet due to the principle of superposition, and the magnetic distances for each magnetic field would increase due to the increased magnetic field magnitude from the two magnets.